Interviews are fun until they're not. You're given an array, let's call it A, which has n elements. You're given another array, let's call it B, which has m elements. And m is less than or equals n. You have to find out how many consecutive m-sized subarrays of A has at least k such elements that also exist in B. Last night, when I fell asleep, I had a dream that I'm in a coding interview, and I was asked this question. My mom literally thought that I was singing the lyrics of Body by Megan Thee Stallion during sleep because she heard me saying num 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 eat it up. But what I was actually doing was panicking because the solution I presented was of time complexity n into m. And the whole time I was thinking that this isn't going to work because both n and m can reach up to 2 into 10 raised to the power 5. So out of panic, I was repeatedly saying O of num, num num, I need to eat this up, and present an optimized solution. The solution I presented earlier was quite simple though. I made a frequency map out of the array B and applied sliding window on array A. So I iterate over the array A, put the elements into another hash map or a frequency map, and as soon as the window would complete the size m, I'd compare the frequency map of array B and array A and find out the number of common elements between them. If the number exceeds k, that means the specific subsegment or the window is eligible to be counted in the final answer, and I'd increase the final answer count by 1. Since array A size is n and I have to choose m consecutive elements out of it, there are a total of n minus m plus 1 windows that I would have to iterate upon. Nevertheless, I'd have to iterate through the entire array A in order to process the windows. Also, for each iteration, the comparison would cost me another m iterations in the worst case. That is, let's imagine that for a specific window, all the elements are unique. I'd have to iterate through all the m keys of A's frequency map and then check the count in the B's frequency map. So the overall time complexity of the solution is O of n into m, which is quite inefficient. The shocking thing is that that's all that happened in the dream. So I woke up and I was glad that it wasn't a real interview. But then I wondered, what if it was a real interview? I'd have to present an optimized solution. And so after my regular morning routine, I spent some time thinking about the optimized solution. And gladly, I was able to come up with one. Imagine that the window size is 100. So first window, that is a total of 100 elements processed so far, and a hash map comparison. Now, as soon as I visit the 101th element, I'd remove the first element from the hash map and put the 101th element in the hash map and perform another hash map comparison. In the whole process, the only thing that changed was the frequency of the first and the 101th element. The remaining 99 elements still stayed of the same frequency. So a complete hash map comparison sounded quite like an overkill. So I thought that let me do only the hash map comparison for the first window. So for the first 100 elements, the window completes and I do a hash map comparison. And I will store the count of common elements in a variable. Let's call it common count. Now when I move the window to the right, I'm getting rid of the first element. So I'll remove it from A's frequency map and update its frequency. Now imagine that the first element is also present in array B. What do you think will happen if the updated frequency of the first element, which is now out of the window, is less than, equal, or greater than its frequency in B's hash map? Let's take an example. Let the first element be 29. In hash map B, 29 is present 5 times. In hash map A, 29 was originally present 4 times. Since we got rid of the first element, 29 is now present 3 times. 3 is less than 5. It means that the first element was relevant. It was contributing in the count of common elements between array A's 100-sized subarray and array B. So what we would do is decrease the common count by 1. What if the 29 was originally present 6 times, but after getting rid of the first element, now 29 is present 5 times? So before, 29 was commonly present 5 times, and now also it's commonly present 5 times. No difference, which means that the first element was always free to not contribute. Same goes if the frequency of 29 after getting rid of the first element is still greater than the frequency of 29 in B's hash map. So in the greater than or equals case, the common count would stay intact. Now comes another point. Since we are moving the window to the right, we're also adding a new element to the frequency map. So we'd update the A's hash map with the new entry and compare the frequency of the new element with its frequency in B's hash map. Again, the same question. What do you think will happen if the frequency of the new element is less than, equal, or greater than its frequency in B's hash map, provided that the new element is indeed present in B? Let's say that the new element is 29. In B, 29 is present 10 times. In A, 29 was present 8 times, but after adding the new element into the window, 29 is present 9 times, which means that the new 29 is actually contributing and increasing the common count, and hence we will increase the common count by 1. What if 29 was present 9 times, but after adding the new element, 29 is now present 10 times? It means that the new 29 is actually contributing, because earlier we would have only gotten 9 commonalities for 29, but now it is 10. So in this case also, we'd increase the common count by 1. But what if 29 was present 10 times and after adding the new element, 29 is now present 11 times? It means that the new 29 is free to not contribute. Array B has 10 29s and array A's new window has 11 29s, so the common count would still be 10. So in this case, the common count would stay intact. And that's it. As we move the window to the right, we just update the frequency of the old element, update the frequency of the new element, and compare those frequencies with hashmap B, instead of comparing the entire hashmap A with hashmap B. This means that we are completely eliminating order of M part. We did the entire hashmap comparison only once. So the overall time complexity would be reduced to order of N plus M, which is way efficient than order of N into M. A sigh of relief, because now I feel ready if this question comes in an interview, whose possibility, by the way, is likely equal to the possibility of me getting a job at Google at NYC. Besides, what's the future state of coding interviews? With AI in the picture and candidates getting an opportunity to cheat, how it's all gonna work out? So many questions. Until another day. Did you like the question? Do you have an alternate approach or intuition? Please share it through a comment. Thanks for watching.